So I'm gonna continue what happened yesterday, and we stopped exactly at the moment when I presented you a picture of some person. I told you his name. His name was Rosy Gasket, and then I announced that plenty of people discovered him with different motivations, and we stopped. So let me remake the portrait and recall you the construction. There was just a triangle. Since we always worked with a three-dimensional case, when there was 3 parameters with additional renormalization conditions, so we had a triangle, and we agreed that if the largest person is, say, I order them in this way at the beginning, and if the largest one was smaller than the sum of 2 others, then we just stopped. I will call this situation the whole. I will explain later why. But then, if it was not the case, we iterated the procedure. The procedure was as follows. We had to subtract the sum of 2 other people from this one, and the 2 who were not the largest, they preserved. And then we reorder them in accordance with their current values and continue the procedure. And so there was a kind of iterated procedure that produced a fractal, even if right now I am not allowed to use this notion, because usually fractal means that the Hausdorff dimension is supposed to be less than the dimension of the object, so less than 2, and I did not explain it at all why it would be the case. But in any case, what we got is somebody who is very similar in his structure and appearance, and moreover, who is just topologically equivalent to a Sierpinski triangle. However, not just a Sierpinski triangle, it would be too easy and too nice in some sense, because what happens is the following thing, that in Sierpinski case, at each step, we would just remove the triangle, which is a 1/4 of the original one, and then we iterate it with a rescaling, yes? So it's always a fixed part of the original triangle. However, in our case, the shape of triangles with time will become distorted. So instead of being a kind of a triangle with a 60-degree angle, they will start to look like this. More and more distorted. And so the question about the measure of the attractor, the Hausdorff dimension of the set, etc., these questions become much less trivial than they would be if we would work with a Sierpinski triangle, because we cannot really apply some standard argument in this case. So the person is named the Rosy Gasket. And as I told you yesterday, it appeared in literature at least 3 times. So for the first time, Lebesgue in 1991 was working with pseudo-groups of rotations. Basically, he was developing some more explicit version of Riep's theory for free groups action for R3s. And he discovered this kind of fractal in his baby example. And already in this paper, he was able to prove that the Lebesgue measure of the Rosy Gasket is equal to 0. But historically, it's not completely true. What happened is that in the paper by Gilbert-Levitt, there is a lemma attributed to Jean-Christophe Yoccoz. So it's Levitt, but with a contribution of Yoccoz. Then the same fractal appeared in the context of Novikov's problem, the problem I will formulate a bit later, in the work by Ivan Dynnikov and Roberto Di Leo in 2008. They did not think at all about any interval exchange transformations. Also, they were working in some topological framework, but they got exactly the same picture, and they reproved the same statement. But their proof was pretty much different from what Yoccoz suggested, since they are people with a very different background. And also they made numerical estimations for the Hausdorff dimension. and it's supposed to be equal to 1.7. Then later, in 2013, it's the year when the paper was published, but I think it's just a technical question. Like in 2011 already, Pierre Arnoux and Stepan Starosta they published a paper where they were working with a fully subtractive algorithm. It's one of the versions of multidimensional fraction algorithms, and symbolic dynamics in the same style as I tried to present yesterday. Maybe today I will spend 5 minutes to explain it better. But you remember all this business with substitutions, Arnoux-Rosy words, etc. So they were working in this framework, and they also discovered the same fractal. And they gave him a name, the Rosy Gasket, and also reproved the fact that the Lebesgue measure is equal to 0. And again, it was a new proof. So, and in this paper, Pierre Arnoux posed a few questions about this object. First of all, since we already know that Lebesgue measure is not good to work with this object, a very natural question is to find some other invariant measure that would serve our purposes. Because as we know, we need to understand the dynamics of Arnoux-Rosy interval exchange transformations, for instance, and all interesting parameters live in some subset that we are not able to touch in some sense. Every time when we enter the room with our Lebesgue measure, it's just too big. And so we are sent away. So we need some nice invariant measure. And Pierre Arnoux asked for the one. And he also asked about some precise estimations for the Hausdorff dimension. In particular, he asked rather it is strictly smaller than 2, at least. Like if we are allowed to call him fractal or not, basically. And finally, the same person was rediscovered again, but it's not completely fair to say that we rediscovered it because I was already informed about all the previous steps. So basically what happened that this work by Dynnikov and Deleo was reinterpreted in a much more dynamical terms by Arthur Avila, Pascal Hubert, and myself. And we were able to prove first that indeed the Hausdorff dimension is strictly less than 2. So Arthur Avila, Pascal Hubert. And it's 2013, we proved that Hausdorff dimension is strictly less than 2. And in the next work, we constructed a natural invariant measure. When I say natural invariant measure, it looks very non-precise what I mean. So I will be back with a precise construction once I explain you these interpretations that we used, because the object we were working with, it's different from the objects that appeared in the previous papers. But just to advertise how good our measure is, I would tell you that first of all, it's ergodic. It's not just invariant, but it's also ergodic with respect to this algorithm that generated the Rosy induction, the Rosy gasket, sorry. And the second point, it's more the cocycles that we would associate with our dynamical system is log integrable. So we were allowed to use all the advantages of Asyledi's theorem and define some Lyapunov exponents, etc., etc. So when I say invariant, I mainly mean that it suits very well all the dynamical purposes people could invent in this context. So now let me explain what we did and introduce a new object, which is called systems of isometries. Again, in this business, it's always the same story, that plenty of people discover the same object. independently from each other, write papers on different languages, and then finally they meet and understand that it's nothing else but the objects they already had. So this guy was born in 1994 in France, and it was a creation of Gilbert Levitt, Damien Gabarieux, and Frédéric Paulin. And they were working on some presentation of the Rips theory for R3s. So it's a pure geometrical group theory work. So what is the object? It's a very natural generalization of interval exchange transformations. I will give first a general definition. That let me recall how we define the interval exchange transformations. We said that we have an interval of a real axis, and we have two collections of subintervals. And each subinterval from the first collection had a pair and a second one, such that they would have the same length. And these were all supposed to be partitioned. And so between each two intervals of the same length, we just had an orientation preserving isometry. Yes? So now we do absolutely the same. We take the interval of a real axis. We take the collection of subintervals. But we remove this restriction that it is necessarily partition. So what we would get is the following thing. For instance, this is the first interval. This is his couple. This is the second interval. This is his couple. And then it could be the third interval here. And his couple would live here, and so on and so forth. So we have AI. It's a collection of the intervals on the top level. BI is a collection of the intervals on the second level. For each I, AI is equal to BI in its length. And there is a phi I, which is orientation preserving isometry. Of course, this map is not one-to-one anymore. It's not just a normal map from the interval to itself. However, even for this object, we still can define the notion of the orbit of such a system. We can take one point and look to all the images it will have under our identifications. For instance, since it's covered by you guy, it's supposed to go somewhere here, but there would be, I don't know, let me find one more person that covers it like here. It could go somewhere here, and then it would be another image of X and so on. So one point can have many images, and it's not forbidden. And the structure of orbits of this thing can be quite complicated. And of course, we can have like finite orbits. We can have orbits with cycles and so on. And the most interesting case corresponds to the situation when all our orbits are still everywhere dense. So they are trees and they are everywhere dense. And this kind of situation in geometry group theory is called the thin type. Thin case when all orbits are everywhere dense trees. Everywhere dense trees.
So this is piecewise isometry, right?
Yes.
And so if that point X chooses blue interval, then does the whole blue interval goes to blue interval? Or
no, but the whole blue interval goes to the, I mean, each point can have many different images and it will follow all of them. You will have a tree as a...
Oh, so it's not,
you do not put
a map, it's like correspondence.
Yes, yes, there is no map anymore, but it's just a kind of identification when one point can have many images and it will preserve all of them. You do not choose anything in this way.
Yeah.
So the general theory is about the question, what should you say about the length of the parameters? So you need much more parameters in this case, because for each interval you need to know its length, but you also need to know where it starts and where the image is located. So the general question is very similar to the one we had for interval exchange transformations. When we will have thin system of isometries, when, in a sense, what kind of condition one needs to put to the length of the parameters. So what kind of part of the parameter space corresponds to this thin situation. And in general, it's a very interesting open question. It is not solved yet. But we will deal just with a kind of a baby representative of this family. So I will show you the family we will work with. And for this family, the answers are known. So what we have just 3 intervals. So 3 intervals and their images, in total 6. And they're located in a very special way. So everybody on the top level should start in 0, and everybody in the bottom level should finish in 1. But it's orientation preserved in isometry, be careful. So 1 and 0, they are not identified with each other. This is 0, this is 1. So 0 is identified with this, and this point, with the leftmost points of the intervals. So we will have 3 lengths, say lambda 1, lambda 2, lambda 3. And already in a general context, it was proved a few times that in order to have the thin case that interests us, so the situation when all orbits are everywhere dense, we have to put a restriction that their sum is equal to 1. So the object was discovered by Leavitt, Gaboriau, and Paulin, but it was later in 2008 rediscovered by Dynnikov, who was so much non-informed about this work of Leavitt that even gave a different name to this object. So later we had to change our way to call it, because we understood that people are already working with it very actively. So in any case, we have this guy, and both Leavitt and his co-authors and they were able to prove we need only to work with the situation that the system is renormalized if we want to have thin case. And in order to understand how do orbits behave, we would like to introduce some analog of the Rosy induction to them. If we have, yeah?
So you're saying thin case is when the orbit is dense, right?
Yeah.
But here it just seems that everything is left to the right side. No matter what you do, you will never come back to the left side. So
no, but the point is that when you live here, the past, like top and bottom, they are not distinguished in some sense. In the sense that if you live here, you will be identified with points here and then go back. I mean, you can go to the past if you want.
always in all cases, or
no, always in all cases of systems of isometries. It's always the case. So let me explain now the analog of the Rosy induction that is supposed to be our main tool to understand the behavior of orbits of this person. I will explain it in this baby case, but in general it's not much different. So the idea is very similar. As you probably remember, what we do in the Rosy induction, we go to the rightmost end. We choose these 2 people who live on the bottom and on the top floor. And we decide who is stronger, who is longer. And the strongest one, he will survive and preserve his place, while the one who has to lose, the weaker one, he will move. So here the same thing happens. We arrive to the rightmost end. We choose the longest person, he will be the winner, and he will force 2 others to move away. So how will they move? They will go to the rightmost point of his partner here. So on the top level, everything preserves. And on the bottom level, these people have to go have to move, while this guy first preserved his position, but then this wing could not be free for him, so he has to be cut, because there is a part now which is covered by only 1 interval, so obviously it's not informative from the point of view of the orbit behavior. So we will cut here, and we will get the following situation that we have. This interval, this white one actually is even not the longest one anymore. So yellow is as small as it was. One, he went here because we cut a good part of it. In this particular case, I mean, when we have just 3 intervals that are arranged in the way I explained, think about it just as a first return map to this interval, in some sense. But I prefer this more detailed and more clumsy presentation, because if you work with a general system of isometry, it's not always the case that you can really think about it as a first return map on some interval. It can be slightly more tricky. So let me write precisely what happened here. First, I would like to convince you that nothing happened to the orbits, in the sense that those who were infinite, they stayed infinite for this new person, and those who were finite, they stayed finite. Because what we did, we never kind of changed anything crucially. We only worked with the points that were at the same orbit in any case. We did not add any orbit. We did not remove any important orbit. And then what happened to the lengths of our person? So we have lambda 1, lambda 2, lambda 3. Let's assume that lambda 1 was the largest and lambda 3 was the smallest. Then the new length of this white person, who was the largest, is the following. Due to this condition, this point is the point lambda 1. Is just 1 minus lambda 1, so lambda 2 plus lambda 3. So a new length of this white person will be just lambda 1 minus lambda 2 minus lambda 3. While lambda 2 prime is just equal to lambda 2, 3 prime is just equal to lambda 3. So you have a matrix like 1, 1, 1, 0, 1, 0, 0, 0, 1, up to the order of the lines, because, for instance, already on my picture, for the next step, I will need to change their order, because the blue one became longer than the new white one, okay? And if you were attentive yesterday when I was a bit messy discussing the Arnoux-Rosy interval change transformations, you probably already recognize the matrix. You can ask me what happens in case if the triangle inequality is not satisfied. With this Arnoux-Rosy business, probably it was not so explicit to understand what was going on. But here it's much simpler, and it's very easy. If lambda 1 is less than lambda 2 plus lambda 3, then a part of our interval will not be covered. We will have a hole in the center, yes? Because this lambda 1 is just less than 1/2 in this case. So there is a part which is not covered by anybody. But if it is the case, it means that here we will for sure have finite orbits. So we are not in the thin case, obviously. And then once we iterated the procedure, we will need to ask ourselves again what happened in the middle of the interval, if now we cover all the points we need or not, if there is a hole in the center. Due to our combinatorics, the hole cannot appear anywhere but in the center. It's the only position which is dangerous. So that means that we have only two opportunities. Or at some point we got the hole in the center, and then that means that we are in a non-thin case, or we never got this hole in the center, and so we can continue to iterate. Okay? So this means that thin systems of isometries, in this particular combinatorial case, where do they live? In the parameter space, just in our favorite person, Rosy Gasket, because that's exactly the way how we built it. There is a slightly more delicate point, because when I was doing all these procedures, as usual, I assumed that my lambdas are rationally independent, because if not, I would be in troubles how to subtract them from each other and so on. While when I was discussing the Rosy Gasket, I was not specifying what happened to these rational relationships among the lengths. But in reality, it's much more simpler than it could appear, because what would happen that one can prove, it's a theorem, that all the rational dependent points, they will live on the borders of some triangles. And so if you consider the Rosy Gasket as an open set, then you do not have this problem, and you can assume that all your lambdas are rationally incommensurable. So, okay, now since we understood how it works for systems of isometries, probably I can explain you a little bit what to do to show that the Lebesgue measure is 0, because it looks like I don't prove any single theorem in my course. It's probably not very good. So there are plenty of proofs, but the idea is always the same, that how do we define the Rosy Gasket? We consider this linear map. we projectivize it because we have this renormalization condition, and we have to work with this projective map that is defined by our matrices. So in such a case, what do you need to understand what happens to your attractor are just two things. First, you would like your map to be expanding enough, in some sense, to be sure that every time these small cells, they indeed decrease their size. And the second important ingredient, it's called the bounded distortion condition, is exactly a condition on the distortions that you can control due to your Jacobian, how much they are distorted at each point of the iteration. So the first point, it's in reality is not so automatic, because with this definition of the induction, I will have fixed points, obviously. If this first interval was incredibly long, I will always have the situation when the matrix is like that, and close to this vertex 1, 0, 0, we will have always Jacobian close to 1, which is not very good. But there is a solution for it, and then I need to ask you a question, because I don't know if Pascal explained how did the Zurich acceleration work or not. Okay, then I will say a few words about that in this case, and it's very useful for interval exchange transformations as well. So as you can see, this algorithm is pretty much similar with the standard Euclid algorithm of division of numbers, because what do? You just subtract the sum of these two people from the largest person. So as in case of Euclid algorithm, you can have two strategies. Or you subtract and subtract and subtract up to the moment when they change their roles, or you do it all in one step, exactly arriving to the moment when you have to change their roles. So here we will do the same. We can accelerate our induction and consider a step of the accelerated induction, the one that is like you look at your lambda 1 over lambda 2 plus lambda 3, and you take the integer part of it and you call it n. And so you consider lambda 1 minus n over lambda 2 plus lambda 3, because you know for sure that up to this moment you can iterate at least 10 times and they will not change their roles. And so you call it lambda 1 prime, lambda 2 is lambda 2 prime is lambda 2, prime is lambda 3. But since it was the integer part, you cannot make one more step, so you know that they're supposed to change their role at this moment. So in reality, your lambda 1 will become one of your lambda 2. Lambda 1 prime will be equal to lambda 2, and then you have a choice. It can be that here it will be lambda 2 and lambda 3, or they can be in the different order depending on how it worked. In any case, you can easily check that the Jacobian of this map already will behave fine. And what does it mean on the picture that we draw? It just means that we make a very precise partition. So we do not look at the whole triangle here, but we make it smaller and smaller. In the vertex itself, we never leave, but we can understand much better in which triangle, which is distinguished from the vertex, do we live with this activity. And so we can make more precise evaluation of the Jacobian in the vertices of this new triangle. Is it understandable what I'm saying? So I just wanted to say that in reality we never live precisely in this point, but we can live very close, but we can measure how close we are using this n, because this n is exactly a measure of how close our lambda 1 is to 1. So we can say that we are not in this point, but between here and here. And if we know that we are between here and here, then our Jacobian are already distinguished from 1, and we can have a uniform boundary for it. And this uniform boundary will guarantee that the map from a small triangle to a big one will be expanding with some uniform constant that did not depend on the choice of the triangle. So this thing is called acceleration. And a very similar idea for interval exchange transformations was suggested by Anton Zurich. So for interval exchange transformations, the same idea is called Zurich acceleration. And in our case, it does not have any name, but still it's very efficient. And there is one more important point, which helps us to estimate the distortion of these Jacobians. What does it mean to estimate the distortion? It means that if we take 2 points who already live in the same small triangle, which I will call a Markov cell, because it's indeed a Markov partition, they are from the same cell. And I would like to understand what happens to the ratio of the Jacobian with these 2 points. So I would like to find some uniform constant that will be responsible for the distance. Then I'm writing f as a map. But you can also consider, it depends on the direction, if you go from a small triangle to a big one or on the opposite. So sometimes you have to write f, and sometimes you just measure the distance between 2 points. So this property, if we have it, if we can find such a uniform C that will not depend on a Markov cell, then this property is called bounded distortion. And it's a way to control how much exactly the shape of these triangles that appear is distorted. And if these 2 conditions are satisfied, the expansion property and this kind of thing, then there is a very standard theorem which is attributed to Régnier and other people of Hungarian ergodic school, where they showed that in such a case you will have an invariant ergodic measure. But in our case, what does it mean? That if we know that basically Lebesgue is this invariant measure, it means that every time we removed something of a positive measure, and still we are supposed to have something of the same measure. So it means that, like, we had some measure of our person was mu x, then we multiplied on some constant which is smaller than 1 and got again mu of x. It could be true only if C is equal to 0. So that, sorry, not C, but C is less than 1 but more than 0. So mu of x was equal to 0, so we had something of 0 measure. And this is basically the idea how to show the fact that Lebesgue measure is 0. This is a strategy that Pierre Arnoux and Starosta were following. Other people had different approach, but it was kind of, this is generic way to prove this kind of things. That's why I showed. And their approach depended a lot on a particular dynamical system. Yeah.
What is F? Is it one of these operations?
Yeah. Well, F is our projective map associated with this linear one. So you make this procedure, and then you need to renormalize because you want their sum always to be equal to 1. So this is F. Okay. So now we stop to discuss the Lebesgue measure of the Rosy gasket. I hope that I convinced you that the system of isometries approach was probably the most illustrative among all the others that appeared to this person. And now it's time for me to explain you briefly how did we start to study these systems of isometries with Pascal and Arthur. We were pretty much inspired by Untitled in this context. Why did we start to care about these systems, and in particular about this family? And this is my first goal, and also I would like to explain you how this family itself is connected to Arnoux-Rosy interval change transformations. Because it's not like just there's the same parameter space where different dynamics could happen. In reality, it's just always the same topological thing. So I will explain you in a few seconds. So first, let me associate with this system of isometry a 2-dimensional complex. I would like to make a suspension. I think Pascal explained a little bit how to build from an interval change transformation a surface. But he did not follow standard Witch approach, but just use polygons to glue. And here I would do a different thing. So I want really to define a suspension complex. It was already described in Witt's paper, because in geometry group theory, it's a particular case of band complexes. So what we do is the following thing. We take our system of isometry, and we collect 3 bands. I would like the width of these bands to be equal to the length of my intervals. So if I had here lambda 1, lambda 2, lambda 3. The vertical lengths right now I do not fix, I don't care that much about them, some positive numbers. And I want to put a vertical foliation on them. Well, it's not so vertical, but it's supposed to be. And then I glue them to the support interval of my system in a way that this up horizontal side will go to the top level and the down horizontal side will go to the bottom level. So what I get is a two-dimensional complex, obviously. Okay? So we have an interval and we have like 3 bands going like that, and then they travel and they come in this way, and so to the support interval. And there will be a vertical foliation on this two-dimensional complex. And the behavior of leaves of this foliation will exactly coincide with the behavior of orbits. Because if 2 points belong to the same orbit, they just live on the same leaf of the foliation on my two-dimensional complex. So the first idea I have is that I will now present informally some way to build a surface from my suspension complex and to define a foliation on this surface in a way that the behavior of the leaves of foliation on this surface will coincide with the behavior of leaves of the foliation on this complex. And so I will use these systems of isometry to study the behavior of leaves of the foliation on this particular surface. Okay? Why do I want to do so? Because there is quite a famous problem in mathematics that is open for a very long time, where this approach is very efficient. And so now it's time to present the third part of our title, Novikov's problem. We will explain what does it mean and what can we do with this two-dimensional complex. So I state Novikov's problem in a generic way, and then I will reduce myself. So Novikov's problem. It was posed by Sergei Petrovich Novikov in 1982. So what did he have? He had a closed homologous to Z. If you don't know what homologies are, you just ignore this. So first homologous to 0 surface that is smoothly embedded in three-dimensional torus. And we have a vector which is non-zero. So this vector indicates a one form on three-dimensional torus in the following way, that you take angular coordinates and just give the vector components as the coordinates for this one form. But then this one form can be restricted to the surface we deal with, and this restriction will give us another one form. So this one form defines the foliation on M. And we would like to understand the asymptotic behavior of leaves of this foliation. For those who are not very used to work with foliations on surfaces and don't want to imagine what does it mean to be embedded in three-dimensional torus, you can consider the following picture. You can take a three-periodic surface. Three-periodic just means that it's invariant under translations on vectors from some lattice. So you get three-periodic surface. And then once you have that, you consider the family of planes which are orthogonal to the same vector h that we already fixed before. and you would like to understand the asymptotic behavior of sections of this surface, three periodic surface by the plane from this family. It can be slightly easy to imagine. So why in general things could be non-trivial? What kind of possibilities do we have? So as a typical surface in this context, you can imagine, for instance, that you take kind of a fat cross inside of the cube. You understand? You take a cube and you take 6 axes in the middle, and then you make them fat. You replace by cylinders and make it all smooth. So if you would consider the section of such a person with somebody who is parallel to the edge of the cube, you will get something closed, some just circle that comes from the section of your cylinder. Yes? So this case is called trivial. Of course, it's not very interesting to work with something closed. Another possibility that you could have if you would move slightly your thing is more exciting. In this case, you will have, in this description, you will have a slightly distorted line. By slightly distorted, I mean that you have a width of you have a band of a finite width, and you have your trajectory always live inside of this width of this band. Sorry. Why you could have something like that? The reason is as follows: that by the separatrices of your foliation, your surface is cut on a tori with holes. So you have many components of genus 1. And on each of these components, or you have something finite, or you have a rational winding. So this on a torus. So this irrational winding corresponds to this case, and that's it. But sometimes you can have something much more exciting. When you have a component of genus at least 3, genus 2 will always split into 2 components of genus 1. But sometimes you can have a component of genus 3 where your foliation is minimal. And if you look at the interpretation in terms of the plane sections, it means that you will get some curve that behaves in a quite unexpected way. It does not want to have such a strong asymptotic direction, but it goes everywhere around the plane in a type of piano or dragon curve, something like that. And this behavior is called chaotic. And so the interesting question that remains open in Novikov's problem is to find and to understand the chaotic behavior. So what was done by previous participants of Novikov's, members of Novikov's school in this direction? Well, this case that I indicated here is called integrable. And it was discovered by Anton Zorich in his first paper in 1984. And basically immediately after Novikov posed the problem. And Anton showed that it exists and provided some examples when it could happen. And in 1991, Dynnikov showed that basically this is a generic behavior. And all the other possibilities, I mean the chaotic case, if it exists, it could only live on the measure 0 set in our parameter space. So what does it mean to be a parameter space here? Well, it's enough. You don't know you in reality do not need to know the whole surface to reproduce the picture. You need to know your vector, and you need to know the positions of the saddles with respect to each other. So you can reduce it to some finite dimensional question. You can introduce some parameter space in this context. I will make it more explicit in a moment. But in any case, Dynnikov showed that chaos exists, it's very rare, and integrable is generic. In 1997, Dynnikov discovered the first example of chaotic behavior. And in 2008, Dynnikov found a way to show the equivalence between Novikov's problem and this model with systems of isometries. I will not provide the precise construction. I will just explain the idea because I'm kind of out of time for all the details. Also, I don't want to go deep in topology. But in any case, you just need to understand that these systems of isometries, they are in a kind of equivalence with Novikov's problem. And when I say equivalence, I mean the following, that every time we have an example of a thin type system of isometry, we can use it to build an example of chaotic behavior in Novikov's problem. And when we have a chaotic behavior in Novikov's problem, we can find the system of isometries that would provide us something very similar to it. So when I say that we can build it, I will just explain quite informally what do I mean, how to build the system of surface if we have a system of isometry. The idea is very natural. You replace your support interval by a cylinder, make it fat as a cross in the example I consider.
What are you explaining now? So you want to
I want to just to explain very informally how to build some surface in Novikov's problem if I have a system of isometry. I will not explain you properly why thin case corresponds to chaotic one, but since we already understood that the thin case is connected to minimal foliation on something, I hope that you will believe me in this context. So the general idea is as follows, that you just take a cylinder and then you make holes in the cylinder where your intervals are attached. And then you associate the borders of these holes, you just reglue them in a smart way. So if you had these three, you will have three couple of holes. I will make a better picture in a second. Yeah, and then you associate the borders in some smart way, which is equivalent to the fact that you add some handles. So if you had three pairs of intervals, you will have something of genus 3. And then foliation will come from the fact that exactly we had a vertical foliation on this original cylinder, so we will define a foliation on this surface, and it will give us a foliation in Novikov's problem. I proceed with a more accurate construction, but before I do this, let me explain the following thing. I'm a bit surprised that nobody asked me before, probably already do not listen, because we have a foliation on a surface in Novikov's problem, which is defined by one form, so it's measurable. So what Pascal had to convince you that every time you met measurable foliation on the surface, you should rank and bring interval exchange transformations. Why people did not do this and why we still care about some problem open at 35 years ago, 36 already. If all the technique exists and we even explained you that there are plenty of results about ergodicity, minimality, invariant measures, and you can go much deeply with interval exchange transformation. The reason is, as the something that we discussed yesterday, Keen's condition. Here, if you look at Novikov's problem, of course you can find interval exchange transformation. You take your surface, you take a transversal and the first return map, etc. But this interval exchange transformation will not be generic. It will not satisfy Keen's condition. And the reason for that is that our surface is embedded in three-dimensional torus, which means that if you will write the integrals for your one-form homologies of the surface, instead of 6 different intervals as you are supposed to have, for instance, in case of genus 3, you will have only 3 of them because you will have some restriction every time you integrate over the element of homologies that has 0 measure on this 0 image in this embedding. Every time you have a 0 integral. So if you take C in homologies that has a 0 measure, 0 image, sorry, 0 image in homologies of three-dimensional torus, And you should have this because kind of this group is too little, yeah, too small. So, and you integrate over it, you will have 0. Which implies that if you look at your length of your interval in interval change transformations, you will have some rational relationships. And so all the Rosy induction technique, blah, blah, it does not work. So this is a problem, and that's why people started to find something else, to look for a different approach and so on. Okay, now let me explain maybe slightly better what I would like, how I want to glue the surface and what does it mean. And then it will be more easy to present you where Arnoux-Yoccoz lives here. So I need to look at the picture. Let me take a big rectangle or square, this is as you prefer. There is a vertical foliation on it, and in reality I'm supposed to cylinder, this one that we used to make the support interval fat. So these two sides are identified. So now what I do, I make 3 holes. This is a hole of the length lambda 1, naturally, and I tried to make it recognizable. How do I identify the borders? Okay, so the second one will be here, and this is lambda 2, of course, and the third one is very small, and it lives here. And so now, how do I glue the surface? I hope it's more understandable, because we have to glue the borders in a way as I made, and there is already a foliation which is defined on this surface. And then it's even not so complicated to understand that whatever transversal you take, you will get exactly some interval exchange transformation as a first return map to this transversal, such that it will have some rational relationships with length, because in this picture, of course, vertical position of the interval does not matter. Their order matters, but where exactly you made this hole, it does not matter for the transversal, for what kind of thing you will get. And for horizontal thing, we have only 3 parameters. So obviously, we are supposed to have some rational relationships. The picture I draw, it's only for this particular case that we are dealing with when system of isometry was like that, when everybody started at 0 and finished it in 1. Denikov's construction is more generic. You can define it for a larger genus, yes.
How do you choose the order? You said the order matters, but it wasn't given to you, so you made a choice.
Well, this I want to skip the description, because I mean the order matters to you can order them differently, but the order matters for the type of interval exchange you will get. The combinatorics can be different if you vary the order. In reality, I think that if you order them differently, you will still have what you want, but you have to be attentive. Maybe not every choice is appropriate.
What is the connection between now? I mean, so you have more trajectories on the band complex, right?
Sorry, it's a little.
Because of the order, then your surface only carries some of the trajectories on the band complex.
Well, yes, but what I want to say I think that you can order them differently, and you will still have the thing in Novikov's problem. But my goal now is to show the connection with Arnoux-Yoccoz, and I will not be able to make you a transversal. I'm not sure that if I order them differently, I always can find a transversal such that the first return map on it will give you Arnoux-Yoccoz interval exchange. So I was attentive at this moment. Okay, so hopefully I convinced you that you can build an example for Novikov's problem if you have a system of isometry and you want this system of isometry to be minimal, to be sure that exactly here you will have for minimal foliation on, and you will have something of genus 3. So it will be a chaotic case necessarily because it does not split into components of a smaller genus. So now my goal is to explain why I spoke so much about Arnoux-Rosy interval-exchange transformations if in reality I'm always working on Novikov problem. The reason is very simple, that in reality it's always the same dynamical system. If you restrict yourself to the situation when you work, you take Novikov's problem for the surface of genus 3 and you want always to have a prescribed type of singularities, so you have two saddles that are double saddles. So if you prescribe all the topology here, then always your foliation that you are dealing with, it will be always the foliation that is done by Arnoux-Rosy interval exchange transformation. So theorem, it's Dynnikov, Pascal Weber, and myself. Endless work in progress. So foliation in Novikov's problem. If M has genus 3, and we have two double saddles, so you can, those who prefer to work with strata, they can rewrite it in the way that we live in some particular strata. So this is in one-to-one correspondence with Arnoux-Rosy interval exchange transformation. So explanation. I can provide you a precise transversal that you have choose on this picture to get Arnoux-Rosy interval exchange transformation. I will make a picture, but if you are fine with that, I will not force you to follow me to see how do we return to this transversal. I hope that you will understand the idea. So we start here. We go here, then this point is in reality identified with this point. So we are supposed to go somewhere here. Then due to this fact, we have to jump here, and we go here. And from here, we go somewhere here, which is prescribed. So these points are identified. So how do we compute the way we go back to the transversal is very simple, that you should look at your vertical foliation. So all these points, they will go back all together. But then starting from here, before you meet this moment, all the points go all together. But then those who started to come from here, they will meet this side. So they have to jump here, and they will go here. So they will meet, some of them will meet this part, and so on. So some will jump here, etc., etc. So it's not hard to calculate. And we did the exercise and checked that indeed you can find the Arnoux-Rosy interval exchange transformation. And vice versa, as you see, also the dimension of the sets of parameters coincide, and even the set where these parameters do live coincide. So if you take Arnoux-Rosy interval exchange transformation, then you fix three lengths. Then I always can build a system of isometry of these three lengths. And since we agreed that here parameters live in the Rosy gasket, I will be able to iterate my Rosy induction for systems of isometries forever, because exactly the Rosy gasket, it was his definition that we can do this procedure forever. But if we can do it forever, then we know that the corresponding foliation is minimal. So we know that we are in Novikov's case, and we can build a picture like that, and we will have a chaotic foliation in Novikov's context. So I forgot the word chaotic. It's very important. Okay, so hopefully I explained you why we analyzed both systems together at the same moment. Now I have to still have a little bit of time, so I will go back to what I said before when I told you that there is some invariant measure which is natural And probably did not look natural at all to you. So now it's time for me to explain a little bit who is this measure and how we found it. So in order to do that, I have to define a suspension flow. It depends on your choice. What do you want to suspend? If you are a great fan of suspension of interval exchange transformation, you can suspend Arnoux-Rosy interval exchange transformation. If, like me, you prefer this model when you have a real Rosy induction instead of some first return map somewhere on the circle, then you can think about the band complex I already defined and think about the suspension flow, which is a discrete version of, like a discrete version can be presented by this complex. And then I will define a standard suspension. So what happens with this suspension? Let us take the complex I built with so much effort and apply the Rosy induction to the whole complex, not just to the intervals as we did before. So we need to care what will happen to these bands. And of course, in the sense of vertical length of the bands, nothing will change for people who lost. They just preserved their lengths. Sorry, I made a mistake. Nothing happened to their horizontal length, but to the vertical something happened. And on the opposite, for the person who won, his vertical length preserved, nothing happened to it, the vertical one, because we just cut a part of it, but a horizontal part. We removed this part, but this part stayed and the length did not change. But these two guys, they were supposed to travel. Before, we went directly from here to here, but now I apply the Rosy induction. So I force this couple to move. What does it mean to move? It means that now first we go as we did, and now we have to take this band to go to their new position. So what will happen? Let me write what will happen to their vertical length. So for the first one it will preserve, but the second one will become longer. Because now the second interval, in order to find his current position, he needs first to go where he was, then meet there this first interval, and with him go to his real position. So it will become h1 plus h2, and h3 prime will become h1 plus h3. So the matrix we get is something like that. And the people who work with the multidimensional fraction algorithm already probably recognized him because it's fully subtractive algorithm map. So apparently this guy is very famous in some other part of ergodic theory. Yes, but well, he's not. Yeah, he's transposed version of the previous. Yes, it's important. But in this way, he is much more recognizable for those who already met fully subtractive algorithm. So in any case, in this way, we can define the flow similar to Teichmüller flow. We can define a suspension flow for our object. Or equivalently, you can define a Teichmüller flow for the suspension flow for Arnoux-Rosy interval exchange. So how it will look like, it will be think that you take some point lambda. Lambda here is a vector. Lambda 1, lambda 2, lambda 3. And you say that you will identify this with t of lambda t. Who is r? R is the first return, first time of return to the small simplex where we lived. Technically, who is r? R is just length of the largest interval on which we consider the first return map, in the same way as we do for the interval exchange transformation. You can imagine it. So R is responsible for the first return moment. So all the moments who live between the 0 and R, will all identify them together. And we will say that all these points will arrive to the point t of lambda, where t is our induction map that does something with lambda. And so then we fix the time t again. So this is the way how we construct suspension flow. And those who are familiar with the Teichmüller flow and the Veitch flow already probably see that it's exactly the same what people do for the Veitch flow. So Veitch flow is this thing that we defined on the bands, and Teichmüller flow is this one, basically. So now let me say what kind of the measure finally we built, theorem. Avila, Hubert, and myself. We said that there is a measure of maximal entropy for this flow. And it's unique. So once we have a measure for the flow, some measure which is nice, there is a standard approach developed by Abramov and Rochlin, I think like in the 60s, when you can project it to the parameter space where we started, so to the Rosy gasket. So the invariant measure on the Rosy gasket is a kind of a projection of the invariant measure we built here for the suspension flow. So now I don't want to explain what does it mean to be the measure of maximal entropy, because it requires another summer school on thermodynamical formalism. And I think that I'm not able to make it in 10 minutes when everybody is hungry. So I would not try. Informally, what one can think about is that measure of maximal entropy is a measure that counts periodic orbits. So you fix a small cell in your Rosy gasket, and you count all the orbits that go back, all the periodic orbits that go back to this particular small cell. And the more periodic orbits you have, larger your cell is. Less you have, it is less. So the measure of maximal entropy is a measure that counts in the most smart way these periodic orbits, and you can think about it in this way. So what is the idea of the proof? Again, since I don't explain what do we prove, it's a bit strange to explain the details of the proof. But I will say just a few names. So those who are interested can take lectures by Amri Sari, who developed the approach how to build measures of maximal entropy for countable Markov shifts. And since our dynamics was Markovian, so we divided into countable a number of cells, and so on. Our dynamics can be considered as just as a Markov shift on some Rosy graph. Then it's quite natural to apply his theory. And there was another ingredient that is very important, because if you want to construct some Gibbs measure or measure of maximal entropy, you need a potential. And in order to find a good potential, you just need to take your roof function, this first return time to the small simplex that we defined already. But it has to have some nice properties, and this we showed in our paper about Hausdorff dimension, using an approach that for interval exchange transformations earlier was defined by Arthur Avila, Sébastien Guezel. It's always a very hard task not to make a mistake. And Jean-Christophe Yoccoz. So these are kind of two main bricks to build this result. And those who are interested, I suggest to go to the original papers instead of ours, because it's very applicable general theories that people build. Quite advanced, especially in the sense of Avila, Guezel, Yoccoz. Okay, so now the measure exists. And it's time to ask ourselves, well, how can we use it for some dynamical statements? And maybe you remember yesterday I told you that Arnoux-Rosy words are always uniquely ergodic. So here we also discussed, even if I made a bit of mess, showing you just one permutation instead of family, but okay, substitution. So we were discussing that our dynamics is basically coded in case of Arnoux-Rosy foliations by Arnoux-Rosy words. However, it's coded, but not up to the level that you can imply that it would imply the unique ergodicity for Arnoux-Yoccoz foliations. And so there is another theorem that Arnoux-Yoccoz interval exchange transformations or foliations, so equivalently chaotic foliations in this case, are almost always with respect to this measure uniquely ergodic. But not always. There is a counterexample that I built with Dynnikov. So this is theorem by Dynnikov, Hubert, and myself. So we showed that it's almost always the case, but you can find some examples of Arnoux-Yoccoz foliations that will be not uniquely ergodic. So then let me say also maybe just a few words about just a second. What is not known in this context, because we already explained more or less. So for Arnoux-Yoccoz foliations, almost everything is almost always known, because we also studied some mixing properties for them. And there is one more question in this context. People already showed the number 2/3 that appeared in a paper by Vincent Delacroix, Pascal Hubert, and Samuel Eliévre when they were studying diffusion rate for the trajectory in the Ehrenfest model. In Novikov's problem, you can ask the very similar question. There are some plane sections, so you have some curves. And in chaotic case, these curves are pretty much complicated. So it's very natural to ask, what about their diffusion rate? Do we have some weak asymptotic direction or not? Because in integrable case, as I told you, there is a very strong asymptotic direction. But in chaotic case, it could not exist. So it's a question if we can find something that would explain a bit how do these chaotic curves behave. And there is a result by Pascal, Arthur, and myself, where we proved that in this case, when the surface is of genus 3 and we have 2 double saddles, so we can model everything with our favorite systems of isometries. So in this case, we can define the diffusion in terms of Lyapunov exponents in a very similar way to what Vincent, Samuel, and Pascal did for Ehrenfest model. And these Lyapunov exponents even can be evaluated. We can prove that this diffusion rate, so, which is lim sup of log dxxa log t. So this lim sup is supposed to be more than 1.5, but less than 1. Both inequalities are strict. And it all comes from the properties of Lyapunov spectrum of this cocycle, which is defined by the matrix that always appears, this fully subtractive algorithm, if you want. So what we proved is that the spectrum is simple and that it's piezo. So it implies, since this is a ratio of 2 Lyapunov exponents, then these 2 properties imply. Piezo, I mean that one is positive and 2 others are negative, and simplicity implies that 2 others who are negative, they are also different from each other. So with this, it's quite easy to see that the following holds. However, what would be very interesting is to get a real constant here, because like people were able to calculate 2/3, it's very cool, and it's much easier to attract the auditory when you present it with respect to what I need to do to show the inequalities. So we are pretty much interested to compute some of these Lyapunov exponents. Why it's non-trivial business? Because our measure is something which is not very easy to touch. So if you just run whatever numerical experiments, most part of things, they are not informative because they just correspond to non-chaotic case, if you want. So it's not a very simple thing, but maybe today on such exercise, Vincent can suggest you to play with it a little bit, to simulate the measure and then to try to understand what happens to the Lyapunov exponents. And another open problem, which is much more famous, it's just the original problem stated by Novikov. Because whatever we were able to prove, we did it in a very specific case, when our surface has the foliation has very prescribed topology. So if you remove this condition, for instance, that your surfaces are supposed to be double, and you consider more general situation, it corresponds to the fact that for systems of isometries, you remove this condition that all of them are supposed to start in 0, and for instance, 2 will start and the third will be free. So you increase the number of parameters, then immediately the problem becomes much more complicated. So in order to let you feel how much, if you go back to what I was talking about today, you remember when we were discussing that the Lebesgue measure of the Rosy gasket is 0, I told you that there are 2 main ingredients for that. First is expansiveness, and another one is some distortion estimate. So if we allow one parameter to become free, we are still able to apply the Rosy induction and to prove that the corresponding map will be expanding, but we are already struggling to prove the distortion property for it. And so nothing is known, basically, and everybody is invited to join us in this very long fight, because it's like I don't know, I'm the third or fourth representative of Novikov school who defended PhD based on this problem, and the problem is still pretty much open. So you're welcome. And this is kind of the main question one can have in this context. If you have in mind any other models that would be different from this one for Novikov's problem, it's also always interesting. And another question which is related to it but not the same is the fact that systems of isometries are interesting by themselves. You see, Leavitt discovered them without any idea about Novikov with his problems. So one would also like to understand better the dynamics associated with systems of isometries in the case if you have arbitrary number of intervals and so on. And it's already pretty much non-trivial as well, because more parameters you have, less predictable your induction becomes. For instance, this acceleration is much more hard to define. So I think that it's time to let everybody to eat, and I stop here.